We're going to talk about limits at infinity. Now, working with limits and infinity, there's a couple of different things. First, there's an infinite limit, and we'd seen that before, and we will actually be talking about that in a different video. So, for example, as we have the limit as x approaches 0, 1 over x squared, that's an infinite limit. But what we're going to talk about in this section is actually as x approaches infinity. So this is called a limit at infinity. So as we're going to consider this, the limit as x approaches infinity of 1 over x squared, let's first look at a table of values. And as we let x get larger and larger, and we look to see what the function is doing, because we have this 1 over x squared, by the time we square it and then take its reciprocal, we can see that the function value is getting smaller and smaller and smaller. So as x approaches infinity, the function is approaching 0. We could also see this graphically as we move along here and we let x get larger and larger and larger. We see that the function value is getting smaller and smaller and smaller. It's approaching 0. We could also let x approach negative infinity, and since we are squaring the x values here, we see that we would also still continue to get the same kinds of values if this would have been a negative 10, a negative 100, a negative 1000, and we would be approaching a function value of 0. So the limit as x approaches infinity of 1 over x squared equals 0, and as x approaches negative infinity, it also equals 0. Let's look at this one as x approaches infinity of x squared minus 1 over x squared plus 1. We could look at a table of values. This is an even function. Since both of our x's have squares on them, we could put in positives or negatives and we'll get out the same function values. So as we look at this numerically, we see that as x gets very large, f of x approaches 1. We could look at this graphically and also see as x approaches infinity, f of x is approaching 1, and we see as x approaches negative infinity, f of x is approaching 1 again. Now looking at this graphically, we see that the line y equals 1 is a horizontal asymptote, and in college algebra we actually learned about horizontal asymptotes, but we never officially defined them. We kind of just said as you go out on the ends, this is a line that it approaches. Now that we have the tools of calculus, we can actually officially define that. So first let's look and see limits at infinity, our precise definition. So the limit as x approaches infinity of f of x equals L if for every number epsilon greater than 0 there exists a corresponding number m such that for all x when x is greater than m, it implies that the distance from the function value to the limit, so we have the difference here with an absolute value, is less than epsilon. So what this is saying is if we have this limit and we look at L plus epsilon and L minus epsilon, there exists a number m such that if we pick any x greater than m, so any x to the right of this, then we see that the function value is within epsilon of L. So we fall within this band here. Now if we changed epsilon, epsilon is just, we could make it arbitrarily small, and as we change epsilon, and we would need to change m, but now we see as long as x is greater than m, we are going to be within epsilon of L. Similarly, if we looked at the limit as x approaches negative infinity of f of x, that would equal L if for every number epsilon greater than 0 there exists a corresponding number n such that for all x when x is less than n, this implies that the distance from the function to L is less than epsilon. So if we had a given epsilon greater than 0, there exists a number n such that if we pick any x smaller than n and we find this function value, we know that the function value is within epsilon of L. And again, we could change this epsilon, make it arbitrarily small, and that would involve us changing the n, but now as long as we have an x less than n, we know we are within epsilon of L. So we have our official definition for our limits at infinity or negative infinity, and as this happens, these functions could look various ways. This could oscillate, and given some epsilon, as long as we had this number n, we know we're within epsilon of L if we are beyond this number, and it could oscillate above or below. But as you see, if the limit in fact is L, then we would be able to find this M, whether this oscillates or whether it's above, below, various ways that this N behavior could look. Let's look at an example here. Graphically, our function is y equals 1 over x, and we could see that our M then depends on our epsilon, and as long as M was 1 over epsilon, or anything greater than that, we'd see that we would fall within epsilon of L. So our L in this particular case is 0, and so you can see this graphically, that as long as you pick any x value greater than M, you are within epsilon of 0, and our n being if we were approaching negative infinity, and for our function 1 over x, as long as the number was smaller than negative 1 over epsilon, you can see that we would be within epsilon of L, in this case L being 0. Now we can officially define a horizontal asymptote in terms of a limit then. The line y equals L is a horizontal asymptote of the curve y equal f of x if either the limit as x approaches infinity of f of x is L, or the limit as x approaches negative infinity of f of x equals L. So this is an either or both of these could be true. So to have a horizontal asymptote, just as we approach infinity or negative infinity, the limit would equal L. Looking at this graphically, it is essentially what we learned in college algebra. As x gets larger and larger towards infinity, or smaller and smaller, negative infinity, we are getting nearer to this line L that we call the horizontal asymptote, and here we have it defined then in terms of a limit. Okay, let's consider the limit as x approaches infinity of 1 over x to the r, where r greater than 0 is a rational number. We could manipulate this because 1 over x to the r is equal to 1 over x then to the rth power, and then based on the theorem that we've had previously, we know that if we have a composition functions here in a limit, that we can move the limit inside and apply it to the inner function first and then apply the outer function to it. And so when we do that, we have the limit as x goes to infinity of 1 over x and then to the r power, and we already know, as we have just looked here, that the limit as x approaches infinity of 1 over x is 0, and so then if we raise 0 to the rth power, we also get 0. So this one will let us know that anytime we have 1 over x to a rational number and we want x to approach infinity, that the limit will be 0. Now as we approach negative infinity, the same thing then will be true, because we could just change all of this and put a negative on here, and we know that the limit as x approaches negative infinity of 1 over x is 0, and then 0 raised to the r power. So this will also equal 0 when we have the limit.